Okay. Sorry, my computer actually shut down because it's the little plug thing's basically broken, but it's whatever. It'll work. All right, so let's get down to finishing this part up. So now we're going to kind of do the same thing we did before. We're going to like disregard everything that's a 1 because we don't need it mathematically, and we're going to rewrite everything else. Okay, so what we are left with from the top over here, let's make 1, put a little equal sign here, and we'll make 1 math operation. So everything that's on the top of the fraction bars will go up here, and everything that's on the bottom will go over here. So from the top, we see that we have 269.1 from over here. We've got a 2 that's on the top of the fraction bar, and we have the 63.55. And that is, whoops, that's the math operation that we're left with after we simplify everything. Okay? So hopefully that makes sense. All right. Which one of the following particles has a mass that is closest to the mass of oxygen? Okay, this is number 45. So oxygen, an oxygen atom specifically, has a mass of 16.00 grams per mole. Okay, so this is kind of asking you to look at the molar masses of each of these things that they've listed here and figure out what the mass contribution of each one is. Okay, so a fluorine atom does not have a mass value that is similar to oxygen, right? Fluorine has a mass that's around 19 grams per mole. An OH ion, OH minus ion, is going to be 16 grams from the oxygen plus 1 point, this we'll call 1.01, you guys like that better, plus 1.01 grams from the hydrogen. Okay, an H2O molecule is going to be 16 grams from the oxygen and 2.02 grams from the hydrogen. The only one here that really kind of makes sense is, I kind of messed up my, here, do that. The only one here that kind of makes sense is the O2, okay? Oh, not the O2, the O2 minus, because this is an oxygen atom that's missing 2 electrons, and electrons have an incredibly small mass value. So the fact that this oxygen atom is missing 2 of its electrons is not going to really affect the mass of it. It affects its charge, certainly, and significantly, but it's not going to affect the mass value of it. So that is the thing that has a mass value that's closest. Okay. Let's try number 46. Which the number of molecules in a sample of NH3 weighing 8.50 grams. So we want to know how many molecules equals 8.50 grams of NH3. Okay, so the first thing that we want to do here is we want to get rid of that gram value and turn it into a mole value. That's always our first step when we're trying to do any kind of conversion into molecules or out of molecules. So we're going to look up the mass value of NH3. It's around 17, but I'm just going to double check. 17.031. Okay, so we get 17.031 grams of NH3 in 1 mole of NH3. Okay, and now our next step here is we're going to get rid of our moles and we're going to turn it into molecules. So in every 1 mole of NH3, that is going to be Avogadro's number of molecules. Okay, now we do some math. Okay, we get like 3.01 times 10 to the 23 molecules, and that is choice D. So we did a good job. All right, let's look at number 47. A compound contains 29.3% carbon, 57.7% chlorine, and 13% oxygen by mass. Its molar mass is 246 grams per mole. Its molecular formula is. Okay, now the irritating part about doing molecular formulas is that to find a molecular formula, first you need to find the empirical formula. There's no way around that. The nice part about this problem is that they gave us all the percent values. So they've done some of the work here for us. So we are going to start by taking all of these percent values, assuming that they are gram values, assuming we have a 100-gram sample and each value is a gram value. And then we're going to convert the gram values into mole values. Okay, so for our carbon, we're at 29.3. Nice little different colors for each one. Oh, chlorine, not hydrogen. 57.7. And oxygen. Okay, now we just got to math a little bit. You're going to see that I always keep more decimal places than I need to because I like to have those extra decimal places for my pseudo formula to kind of ensure that I get a number that's the closest possible to a whole number. Okay, and these are the values that I'm going to use for my pseudo formula. And for my pseudo formula, I'm going to divide everything by the smallest mole value here, which is oxygen. All right. So we got C. Okay, I'm going to erase my work up top so that we can continue on here. It's nice, right? I erased the work and you guys can always rewind it and go back and see if you've missed it. So. Two point. Okay, so that's our empirical formula. Now, we went over this yesterday, but it's good to remind ourselves constantly that to find the molecular formula, we need to compare the empirical formula mass and the molar mass. So we're going to use the empirical formula to get the empirical formula mass. So that's going to be 3 times 12.01, 2 times 35.45, and 1 times 16. We're going to get that value. That value will be our empirical formula mass. That's 193. Okay, now figure out what the molecular formula is. We have to compare the empirical formula mass and the molar mass. So, I'll use this. Right. So I get my oh, reverse that. What am I doing? So we're going to call that the molar mass up there. Now this molar mass value, that is what you get from the formula. Okay? Not from the formula, from the problem. When they give you the information in the problem, when they told us that the molar mass is 246 grams per mole, they're giving us this value right here. Okay, so we're going to sub in the 246, and the empirical formula mass is the number that we get when we do our math up here. So we're going to put 122.93 down here, and we're going to see what we get. Okay, so we get an n value of 2 when we divide these two numbers out. So we get n equals 2. So when we get an n value that equals 2, that means we're going to take this 2 and we're going to multiply our empirical formula by it. And we're going to apply that 2 to every coefficient in there, and that's going to give us our molecular formula. So our molecular formula is going to be C6Cl4O2. Okay. All right, so that's going to be it for now. I'll come back a little later, I think, and try to do a few more of these. But just keep on working on this review sheet, keep on practicing, and let me know if you have any questions.